my name is Andrew, and yeah, I'm at Aberdeen Science Centre, and today we're going to talk all about space. So I hope you all like space. I certainly do. Jess, who's here with me, also really likes space. So yeah, we're going to get started. One of the reasons we like to study space is to learn more about our planet and other planets. I have got Earth here, okay, and this here, some of you might be shouting out already, this is Mars, okay? To study Earth is pretty easy. That's where we all live. We live on Earth, so if we want to study it, all we have to do is go outside and we can have a look at the soil, we can have a look at trees, we can have a look at different animals, we can look at all sorts of things that we want to know all about Earth. But Mars is a different situation. Mars is a very, very long way away. So if we are going to study it, we're going to have to send things all the way through space to get to Mars, okay? One of the ways we're going to be learning more about Mars is using the Rosalind Franklin Mars Rover, which is going to be launched next year. It's going to be a rover that is going to be going around Mars, and it's going to be investigating and trying to find out more about what's going on there, and is there any comparison that can be made with our home planet of Earth, okay? So we are going to be looking at some demonstrations and working out how we can learn more about space. Does anyone know how we can travel through space? If you can, just send a wee message to us just to tell us how you think would be the best way to get through space. Okay, so we'll be getting some answers. Yeah, there we go, someone's got it. It's a rocket. Now, a spaceship, yeah, a spaceship would be great too. Well, what we've got here is, we don't have a full rocket, I'm afraid. It's just a rocket balloon, okay? So I'm going to show you how this works. So in here, I have got a gas called air. And what's going to happen is, I'm going to let go of the balloon, we're going to see what happens. Now, there you go. It just fell down, all right? But what we had there was the balloon pushed the air out of the balloon, okay? It pushed it out. What happened after that was the air pushed the balloon. So what we end up having is they end up pushing one another. The reason this happens is due to something called Newton's third law of motion. Some of you might have heard of Newton before. Sir Isaac Newton lived a long time ago. He had great big curly hair. He was very intelligent, and an apple fell on his head. But basically, he did a lot of scientific investigating and discovered the three laws of motion. The third law of motion is for every action, there's an equal and opposite reaction. So that's the balloon pushing the air and the air pushing the balloon. There are, of course, other examples. If you have two magnets of the same size and strength and you put them next to one another, where you have both north poles next to one another, what will happen is they will push each other away, opposite and equal. Some of you may really like going swimming. And if you like going swimming, you'll know that you'll have to push the water behind you. And if the water goes behind you, you'll end up going forward. Equal and opposite reaction. Some of you may have baby brothers and sisters or cousins. And you might have, if your baby brother, sister, cousin, whoever, has a sneeze, what might happen if they're sitting on the ground is the sneeze might go that way and the baby might go that way and fall over, okay? So equal and opposite reaction. Useful in everything from explaining why babies fall over to getting rockets into space, okay? I happen to have another balloon, so I feel like we should probably do a second one. 3, 2, 1, blast off. There we go. Now, when you go to other planets, you have to deal with new environments, new things that we don't have to deal with here. Not just on other planets, but also places like the moon. On our planet, we have gravity, and we also have air. On the moon, there is gravity, not quite as much, but there isn't air. I have a feather and a hammer. What I'm going to do with these is I'm going to drop them at the same time from the same height. What do you think is going to happen? Have a bit of a think, and then we can see if we can get a few answers coming in. So I'll be dropping them from about this height at the same time. If you don't know, that's okay. We're just having guesses. Okay, so we've got one answer saying that the hammer will hit the floor first, the feather will take longer. Okay, all right. So getting lots and lots of answers. Excellent. Well, I think it's time to find out. 3, 2, 1. So, lots of you were correct. The hammer took longer, the feather took longer, I should say that correctly. The feather took longer to reach the floor. Now, I saw one of the answers said because the hammer is heavier. We're going to have a think about that. I've got a sheet of paper here, an ordinary sheet of paper, okay? What I'm going to do is I'm going to drop it from here, and I want you to see if you can time to see how long it takes to land on the floor. And I'll do it back here so you can see it landing on the floor, okay? So get ready with any timers you might have. If you don't have a timer, just count, okay? So 3, 2, 1. Okay. Can anyone tell me how long that took? Okay, so 3 seconds. Yeah, I'd say that's about right. About 3 seconds. But yeah, there we go. Between 2 and 3. That's pretty good, everyone. What I'm going to do now is I'm going to change the shape of the paper. I've scrunched it into a small ball, okay? I've not changed any of the weight. I've not ripped a piece off. I've not done anything like that. We're going to drop it again from the same height. And again, I want you to time it and see how long you think it takes to reach the floor. 3, 2, 1. So, 1 second. Yeah. Okay. Even less than that. Okay. So that was, yeah, it took a lot less time. It took about half the time, if not less than that. But we didn't change the weight or the mass of the paper. So why is that? There was something that was making the paper go slower when it was not scrunched up, when it was a nice, uncrinkled sheet of paper. What do you think that could be? Can anyone tell me? It's also the same reason that the hammer and the feather traveled at different speeds. It is spread out. We're getting somewhere that's quite close to the answer. Aerodynamics, that's a fantastic word. So it's not to do with density. Okay, it was gliding, very good. So it's due to something called air resistance. When the paper is spread out, there's a lot of air in between it and the floor, and all that air is going to get in the way, so it kind of has to move out the way of it. When it's scrunched, what will happen is it will fall straight down because there's less air slowing it down. Okay? It's the same with the hammer and the feather. The feather is longer, and what it can do is it can be affected more by the air in the room. When astronauts went to the moon, what they did was they took a hammer and a feather with them, and they dropped them at the same time from the same height. I want you to have a think about what happened, and we will make sure to send you a link with that clip so you can see what happens. Okay? And then think about why it happens. When you go into space, you have to do all the things that you need to do every single day. You need to eat. You need to sleep. You need to drink. You need to brush your teeth. You even have to go to the toilet. So, when you're aboard the International Space Station or on a rocket, gravity doesn't quite work the same. On the International Space Station, due to something called microgravity, things float around. So think about going to the toilet when things don't fall down. Might seem a bit strange. On the International Space Station, when they go to the toilet, they have to use a seatbelt while they're on the toilet. Otherwise, you might float off and you might leave something rather disgusting behind. Okay? It's really important that we make sure to look after ourselves while we're on the International Space Station and make sure things are really clean and we don't have any unnecessary solids or fluids. Okay? I would like everybody to put one finger on the tip of their nose and thumb of the same hand on their bottom lip. Okay? Once you've done that, pull your hand forward and just have a look about how big that is. It's only a few centimeters. That's the amount of liquid that it would take to drown you. Okay? On Earth, we deal with that volume of liquid all the time. When you're having a drink of water, when you're stepping over a puddle, when you're washing your hands. But we don't think about, oh no, someone went to go get a drink of water and now they've accidentally drowned. That's just not something we have to think about. In space it is. When we've got that amount of liquid, it can float around. And if it manages to cover, which it can due to the lack of gravity, it can cover someone's nose and someone's mouth. Now, drowning in water, pretty bad. Drowning in something else that someone has maybe produced themselves is worse. So it's really important that we're able to absorb that liquid and get rid of it and stop it becoming dangerous. What I'm going to do is I'm going to do a demonstration where we're going to think about absorbing water. I've got 2 beakers here and 2 jugs. Inside this jug, I've got some cotton wool, okay? Inside this beaker, I've got some powder, some white powder. And in each of these jugs, I've got 500 mils of green liquid. It's just water with food coloring. It's no fancy potion or anything like that, just so it's easier for you all to see. I'm going to pour 500 mils of green water into each of my beakers, and we're going to see what happens. We're then going to leave it for a second, do another demonstration, and come back to it. So what I want you all to do is have a think, which one is going to be better at absorbing the liquid? Here we go. So, when we were thinking about the liquid, we were thinking about the dangers of space. One of the dangers being fluid getting into places it shouldn't be. Can anyone tell me another danger you might face if you go into outer space? So what sort of things could be really dangerous or a threat if you had to deal with them? Oxygen, okay. Yeah, lack of oxygen, excellent. These are all, you're all going to the same sort of place. Yeah, oxygen is vital for our survival. Really, really, really important. Lack of food, yeah, you definitely need to think about bringing food. Meteorites can be very, very dangerous. Yeah, lack of energy, you don't want your rocket or your spacecraft to stand still. You want to be able to keep moving, okay? These are all really good answers. The one we're going to be thinking about is similar to lack of oxygen. Imagine going out into space without a spacesuit. You would have to deal with the lack of oxygen, which would be terrible. But not only that, but you'd have to deal with pressure. What I mean by that is there's air all around you. Everyone wants to put their hand up and then just move their hand back and forth like that, making sure you're not hitting anyone. You're just making sure that you can feel air moving between your fingers. There's air around you. As air moves around you, what it does is these little molecules, tiny, tiny, tiny bits of air, bounce off of you. And your body kind of pushes back. So there's a balance. The pressure is balanced. If any of you have ever been on an airplane and you've gone, as it's been ascending into the sky, you might feel your ears start to pop. And that's because there's a pressure change. It means that there's fewer air molecules pushing on your body, and your body's pushing back a wee bit too hard, a bit more than it needs to, and that's why it feels a bit strange. Out in space, there's no pressure whatsoever. That means your body's going to push, and there's going to be nothing pushing against it, which is not good. What I've got is a very special volunteer. This is Susie. What we've got is her inside a vacuum jar. What that means is that this tube is going to suck the air out of here, and we're going to see what happens to her. Now, I do understand that some of you might be looking at her and going, oh, that's really weird. Yeah, it is. She does look rather strange. Don't worry about it, though. She is a trained professional. She knows what she's doing. What might happen might make you laugh. It might make you squirm. I think it's pretty funny, and I hope you do too. But what do you think is going to happen when we start to suck the air out of this jar? Any suggestions? So her face will smoosh, interesting, explode. Any other ideas? She will shrivel up, explode, her face will suck it, she will crumple. Oh, well, none of these sound nice, okay? I'd hate for any of these to happen to me. Go flat, her head will explode. Okay, I think it's time to find out, okay? For this bit, the machine is quite loud, so I would advise turning your volume down now. So what we're going to do is we're going to try taking the math out and see if that makes a bit of a difference. I think she's probably had enough of that. She wants to see what happens when we let air back in. Oh dear, not very nice. What happened was, all the air inside Susie and the shaving foam which was inside of her, all that air just kept pushing and pushing and pushing. So it came out of her eyes and her ears and her nose and her mouth and, well, her armholes as well. Not very nice at all, okay? This is not exactly what would happen to you if you went into space without a spacesuit. But it's the closest we can do here within our health and safety regulations. I should say, don't try this at home or indeed anywhere else. But there we are. That's what happens when there is a significant pressure change when you've got a doll filled with shaving foam. I hope you enjoyed it. Anyway, why don't we have a look and see how the green water is doing with the absorption? So, hopefully, you will have made a guess, a hypothesis, to see which one will be better at absorbing the water. So, would you like to post your answers now? So, which one? So, we had cotton wool over here, and we had a white powder here. Okay, so the powder, excellent, yeah. Well, what we'll do is we'll have a look and see what the cotton wool has done. So that's about 400 milliliters of water back in the jug. So it's only managed to absorb about 100 mils. Let's have a look at the white powder. Well, it's not white powder anymore, but there is no liquid left. Does anybody want to make a guess as to what type of powder we've used? So something that's white that is really good at absorbing water. Okay, so we've got one answer, which is flour. It's not flour, but interesting guess. Bicarb or baking powder, again, interesting, but it's not baking powder. It's not washing powder or baby powder. Oh, we do have one correct answer. It's instant snow or magic snow. The scientific name is sodium polyacrylate. Now, we have someone saying powder from a nappy. And that's quite interesting. We were talking about what it was like to be on board the International Space Station and deal with, well, pee. Okay? It's not nice. Astronauts sometimes have to go outside the International Space Station, and they need to put on a very special type of spacesuit that allows them to go and deal with a lack of pressure without being inside a spacecraft. They have to have their own environment inside their suit. And these spacewalks that they go on can last several hours. I want you to imagine going to school and not going to the toilet for the entire time you're at school. Not even at break time or lunch time. Anyone think they might be able to do it? Anyone think they might be able to do it comfortably? I know I would find that very difficult and probably wouldn't be able to manage. So astronauts, when they go on these spacewalks, they need to be prepared in case they need to go. So what they do is they wear a MAG. That stands for Maximum Absorbency Garment. And what that is essentially a nappy. So if they need to go to the toilet when they're going out on a spacewalk, what will happen is it will be absorbed by something inside it, very similar to this, which means, well, they don't have to worry about lots of wee being sloshed around inside their pants. Okay? Right, let's move on to our next demo. When you go up into space, some of you were saying you need to make sure that you've got plenty of energy, that your rocket doesn't stop. It's also really important to make sure that you're able to steer in space. If you go up into space, you want to make sure you get to the right place and you're able to come back home again. That means steering is essential. Does anyone know how you steer a car? What do you have to do? So, what do you need to do if you're going to be driving a car and you want to change direction? What's the first thing you should be, or what is the main thing you need to worry about? Yeah, steering wheel. That is correct. You need to make sure you're using the steering wheel. What that does is that changes the direction of the wheels on the road, which push against the road, and off you go. You're going in the direction you need to. Will that work for spaceships and rockets? What do we think? Can you use a steering wheel and wheels on the outside of your rocket to change direction? Or do we need something else? Are there wheels on the outside of a rocket? No. No, there's no way to do it like that. We need something else. Okay? So what I'm going to do is I'm going to bring out a wheel that is a bit different from a steering wheel. It looks a bit like a bicycle wheel, but it's got some handles on the wheel itself, and attached to the handle, it's got a string, and then there's a handle at the edge of that. If I were to let this wheel go, but hold onto the string, what do we think would happen? Any ideas? So if I hold onto the string, but let go of the wheel, what do we think is going to happen? Okay, so some people think it might spin. Interesting. Okay, it might turn the wheel. Okay, so I think everyone is thinking it's going to spin. Well, let's have a look and we'll see. So what happens is it just kind of dangles there. It's not particularly exciting. However, I've got a second string. What I'm going to do with this one is I'm going to just slot it in here, and I'm going to spin the wheel so that the string wraps around the wheel. What I'm going to do this time is I'm going to pull this string, and then we're going to do the same again. I'm going to hold the other string, and I'm going to let the wheel go. What do you think is going to happen this time? So before we had just that one string there, and we let it go, and it will drop. But this time, we're going to get this wheel going, and we're going to see what happens. So we're getting lots of people saying it's going to spin this time. Okay, let's see if you're right. So the wheel is spinning, but as I do this, what we have here is the wheel starts to go round and round. This is due to something called angular momentum. Basically, this wheel has got so much energy and it wants to use it all. It wants to go forwards, it wants to come round this way, and it wants to keep spinning round and round. It is starting to slow down. That's because, well, the wheel is slowing down. When it was up, okay, when it was vertical, the angular momentum was stronger than gravity. But as it uses up that energy, it doesn't have as much momentum, and therefore it becomes weaker than gravity and starts to slow down. This has got a special name. this type of force. It's called a gyroscope or gyroscopic force. What can happen is on a spacecraft, by having multiples of 3 of this, they can angle the spacecraft in the direction it needs to move. But gyroscopes are used not just in spacecraft, but actually in quite a few different ways as well. If you enjoy playing with a fidget spinner, well, a fidget spinner is a type of gyroscope. That's why if you ever spin it quite fast and then try to move from side to side, you'll feel a little bit of resistance. That's the gyroscopic force that you're pushing against. Mobile phones also have a gyroscope. If you've ever taken a picture and you've been looking at it and you're going, hold on, I want to make it a landscape rather than portrait, and move it and all the wee icons move, that's because there's a gyroscope inside your phone telling it which way is up and which way is down. And helicopters actually use gyroscopes as well. Okay? Gyroscopes are useful in lots of ways, from fidget spinners to steering spacecraft. Now, we're almost finished our demonstrations for today, but we do have one last one that hopefully you'll all enjoy. We've been talking a lot about rockets and traveling through space, and we did have the rocket balloons at the beginning. But I think it's time for something a little bit more powerful. What we have here is an air-powered rocket launcher. What I'm going to do is I'm going to pump up our rocket launcher. We're going to build up some pressure, and then we're going to blast it across the room. Now, you might see that down on the floor over here, we've got a small black sort of box. This is, in fact, a speed camera. So we're going to see how fast we can get our rocket to go. We're going to be looking at it in kilometers per hour. Okay, so a kilometer is 1,000 meters. So have a guess and see how fast we can get our rocket to travel. Okay, we've got about 60, 50 kilometers, 250. 50, okay, quite a big range, but right. I think it's time to test out this rocket and see what happens. Five, four, three, two, one, blast off. So, you all wanted to know how fast it traveled. We had, I think 50 was the lowest and 500 was the fastest. But we reached a top speed of 133 kilometers an hour. Now, that was pretty exciting, but you know what? I've got another rocket. So, we're going to do that again. See if you can guess, and see if we can get a little bit faster. Make some more guesses, everyone. Okay, so we've got quite a few there. So 164, 177, 200. I think there was a 300 and a 500, 490. Okay, lots and lots of guesses. Excellent. Right, well, I think it's time to do our final rocket and indeed our final demonstration of this show. 5, 4, 3, 2, 1. Blast off. So, what do we think? Was it faster or was it slower? Well, we had lots and lots of good guesses, but that one was slightly slower at 122 kilometers an hour. Well, everyone, that is the end of our Destination Space Show. I hope you've enjoyed it. I hope you've learned something from it. If you do have any questions, send them in. Even if you think of one later, you can always tag us on Twitter or come into the Science Centre when you've booked in, or come with your class and ask us then. Thank you so much. And a big thank you to TechFest. And if there are any questions, yeah, on you go.
So we've got a first really good question here. It's, what is the moon made out of?
That is a great question. So that is, what is the moon made out of? Now, some of you might have watched a Wallace and Gromit film, which would suggest it's made out of cheese. It is not made out of cheese, unfortunately. It is made out of rock. It's got quite a few different types of metals up there, a few different types of minerals. There is a little bit of water up there as well, but mostly it's a big, big rock. Okay?
How do you send oxygen to the International Space Station?
That's a great question. How do you take oxygen to the International Space Station? Well, when it was built, they had to pump oxygen into it. But some of you may know that we breathe in oxygen and we breathe out another gas. Does anybody know what gas it is that we breathe out? Anyone want to make a guess? Excellent. CO2, also known as carbon dioxide. Okay, so CO, the O in CO2 is oxygen. On the International Space Station, they have an oxygen recycler which can remove the carbon from carbon dioxide and turn it back into oxygen. So you don't need to keep sending it up. The International Space Station can do that for you. Now, somebody did ask, how fast does a real rocket go? Well, they do have to go incredibly fast. So they do have to go at upwards of 200 kilometers an hour. Jess, would you be able to just double check what the top speed of a rocket is? But they do have to go incredibly fast because they have to just keep on going, and they get faster and faster and faster as they go. Okay, so at their top speed, they can reach up to 365,000 kilometers an hour, so much faster than the ones that we have here. Okay, so we've got another one. What do we make the astronaut suits out of? Well, they're actually made out of loads of different materials. They have got so many important jobs to do to keep their astronauts alive. So they've got, they've got lots of metal. They've got lots of plastic, just for all the clips. They've got different types of fabric to make sure that it's padded and keeps them warm. But one of the most interesting materials in an astronaut's spacesuit is Kevlar. Now, Kevlar is also known for being bulletproof. In space, there are asteroids, so tiny, tiny rocks, and actually some really big rocks as well. But the Kevlar is there to protect them from the tiny, tiny rocks. The tiny rocks can move incredibly fast, thousands and thousands of kilometers an hour. And that means that, well, astronauts don't have the reflexes to get out of the way. So their suit needs to be strong enough so that the rocks will just bounce off and prevent the suits from being burst open or ripped open and letting all the oxygen and the pressure out. So Kevlar is probably the most interesting material that a spacesuit is made out of. Yeah.
Why do you like space so much?
Okay, this is maybe my favorite question. Why do I like space so much? I think there's actually loads of reasons why I really like space. I think, so number one, it's something that you can get involved with wherever you are. All you have to do is have a dark night where there are a few clouds and you can see up into the stars and you can see so far away. You can see just an incredible distance out into space. It changes quite a bit, so you might see shooting stars. Occasionally, you'll see comets, and if you've got a telescope, then you'll be able to see things happening on places like Jupiter. You'll actually see the different rings of Jupiter and Saturn move if you've got a powerful enough telescope. I think things like television and films allow you to get your imagination going. So it means you go, oh, I wonder if there's somewhere that does this. I wonder if there's something that does that. I think as well, there's recently been a lot of development in space exploration and space science. So you find out new interesting things and you end up going, well, if that's happened, then, oh, we should find out more. We should find out more about that. The idea of just floating around in space is just, to me, really cool. It's basically like being a superhero and you can fly. And it's just so different from what we have here that it's really exciting. So I think those are kind of the main reasons that I think space is really exciting. So we had another one, which is, what do astronauts eat? And the quick answer is food, basically. One of the big differences is that crumbs become a real problem out in space. So rather than making food on like bread and making sandwiches, tortillas are much more used because they don't make much crumbs. And the other reason is, up in the International Space Station, there's no point in having a plate because your food is going to float around, so you don't have to do any dishes. But by having a tortilla, a wrap, it means you can put it all together and it's much easier to eat. So we had another question, which is, how do astronauts shower? Quick answer is they don't. When we move around, and we sometimes get a bit sweaty. It goes onto our clothes quite easily, and there's a lot of sort of friction rubbing against us. But when you're out in space, well, because you float around, so do your clothes as well, so they're not quite as in contact with you. So you don't need to clean quite as much. And generally, it's a sort of a cloth sort of situation. You just kind of rub yourself down with it just to get to the areas that need it most. But yeah, you don't need to keep it quite the same hygiene habits as you do on Earth. Just any more?
Do astronauts have a toilet system that gets rid of poo or pee?
Yes. Yeah. So when astronauts get rid of poo, what they do is they they sit on the toilet with a seatbelt, and there's a complex mechanism that basically is kind of like a mega flush. It kind of has an airlock, which means that the poo is kind of separated from everything else, so they can just jettison, so kind of send it out into space once the poo container is full. Now, the interesting and kind of gross thing is that it kind of burns up in Earth's atmosphere. So if any of you have ever seen a shooting star, well, shooting stars are not stars. They are, in fact, things that are moving into the Earth's atmosphere and burning up as they kind of fall across the sky. Now, sometimes they're, rocks, but there is the possibility that if you've seen a shooting star, it is, in fact, flying, burning astronaut poo. So there we go.
Which planet is the biggest?
So the biggest planet in our solar system is Jupiter. But we don't know which one is the biggest planet in all of space because we've not explored all of space, and new planets are being discovered all the time. So it's really difficult to say which is the biggest one, but Jupiter, which is the sort of big white and orange one, so we've got Mercury, which is the closest to our sun, then it's Venus, then it's us, Earth, then it's Mars, and then it's Jupiter. So Jupiter is the fifth planet from the sun.
How long does it take to get to the moon?
Okay, so, well, first of all, if you're using a rocket, it's a lot faster than any other vehicle, because, apart from space shuttles, but we don't really use them anymore. But it takes about 3 days to get to the moon. It does actually change. The distance between Earth and the moon does actually change, which is a bit weird, but that's how space is. There's nothing holding it into place. It's all a bit floaty.
Can any animals breathe in space?
Well, humans are animals, and we, like pretty much all animals, need oxygen. However, there is a microorganism, so a tiny little thing that you can't see unless you have a microscope, so you can't see it with the naked eye, and it's called a tardigrade. Now, tardigrades also have a couple of nicknames. They're also known as moss piglets and water bears, but they're little tiny creatures, and they have got sort of 6 legs. And they're incredibly indestructible. They have just got the survivability that no other animal has. And in fact, what has happened is astronauts, they took some tardigrades up and they popped them into space for 10 days and took them back to see what had happened. And they were able to survive. So, yeah, tardigrades, if you're interested in sort of the idea that there might be alien life, tardigrades would be a good place to start.
Does the moon have an equator?
So, when we think of the equator, that's kind of the sort of the middle of the Earth where the sun shines the most on. So in a way, it kind of does. It would just be sort of the middle of like around the moon in the same way that it would be around the Earth. But it's more of that's more of a human thing that we've decided. There is a ring that goes around the Earth. So as long as we decide, yeah, there's a ring around the moon, then yes, there's an equator to the moon as well.
What is the furthest anyone has ever been from Earth?
What is the furthest anyone has ever been from Earth? Now, I'm not actually too sure of this. We might have to look this one up. It's a really good question, though. But the thing is, we're always looking to try and get further and further out and explore more and more of space. Space is just phenomenally huge. So we're always trying to go to the next big milestone. The big next milestone for us will be going to Mars. We've been to the moon, but I'm not sure, has anyone been further than the moon? So round the back of the moon, okay, and the distance to the moon is, well, it's about the equivalent of going around the world 10 times, okay, so quite far. Now, somebody asked, does it rain in outer space? And the answer is, depends where you are. Around Saturn, there is a moon called Titan. And Titan has, it's not a water cycle because it's not water. It's methane. And there are methane lakes, there's methane clouds, and it does rain methane. Methane, you might have heard about, and is probably most or best known to you as what comes out of your bum when you fart. So yeah, on Titan, it rains farts. So there you go, yeah.
Which planet is the furthest away?
So in our solar system, that would be Neptune. That's the furthest planet from us. But we don't know all the planets. Again, we're finding more and more planets which go around other stars, and so one of those. And yeah, if you discovered a new furthest planet, then it would be one that you discovered, and then someone else might. But again, space is just so enormous that you could just keep on discovering, and we don't know where the edge of space is, so we may never know.
How long can you spend on the International Space Station?
Well, as long as the International Space Station is there, and you don't get thrown off, then I guess pretty much as long as you want. They would have to keep sending you food, but one of the things that they're doing on the International Space Station is they are looking into how do you grow plants in space, and they are becoming a bit more successful, which means that it is kind of going to become a space farm. So if any of you are interested in being space farmers, there could be a job for you in a few years. So someone asked, what are stars made out of? Effectively, it's hydrogen and helium are the two main components in stars. And what they do is they take hydrogen and they kind of create it into helium. And it's something called nuclear fusion, which can generate a colossal amount of energy. So a huge amount of energy. And that's what stars are made of.
Okay, so we still have quite a few questions, but we're just going to ask one more, and we'll drop it on an email with answers to the rest of them. So the question we're going to finish with is, do you think there is life on other planets?
Okay, so we've only got time for one more question, and we've decided to choose this one, and it's, do I think there is life on other planets? And again, this is a really good question. And my answer is I do. I do think that there is life on other planets, but I don't think it is something that looks like us. I don't think they have, 2 legs and 2 arms and can walk and, like have Zoom meetings or have science centers. I think it's more likely that they'll be a bit like the tardigrades I was talking about earlier. I think they'll be very, very small microorganisms, or at least those will be the ones that if we ever make contact with other life forms from other planets, that's what they'll be. As for the very, very far, into the universe, there could be intelligent life somewhere out there, but we've not seen any evidence of it. And we find it really difficult to go any real significant distance into space. And the challenges that we face, another intelligent organism would also face. So unless they've come up with something that has that we've not been able to work out yet, then the chances are we're not going to meet an alien that you can be best friends with, and we can have sort of galaxy sports against or anything like that. But thank you all so much for all your great questions. They're absolutely fantastic. We're going to hand you back over to TechFest now, but keep sending questions in and we will get to them when we can and send them to you via answers via email or Twitter or whatever we find is the best way for you. Thank you.
Thank you. Thanks all for joining us. Just before everybody disappears off, I just want to take this opportunity to say a huge thank you to Andrew and to the Aberdeen Science Centre. That was absolutely fantastic. So much fun, but I learned so much as well. It seems like you guys did too. All of your questions are absolutely brilliant. Like they mentioned there, if you had a question that you really wanted answered that we didn't have time to get round to, don't worry, you can email us, or if you tag us on Twitter, I promise we will get back to you. Although we love that you have so many questions, and it means clearly we need to have Andrew back again some point to do even more space shows and space chat, because there's so much interesting things to talk about. Thank you all for joining us today. If you'd enjoyed today's event, don't forget to check out the rest of our festival programme. This is just day one for us, so we've got a whole week of brilliant shows coming up. So make sure you have a look, and if there's anything that you're not signed into, there's still plenty of time. Like I said at the beginning, this show as well will be uploaded onto our YouTube channel in the next couple of days. If you just go to TechFest Aberdeen, you'll find it, so you can watch it again, or you can share it with all of your friends and family. Once again, thank you so much, Andrew. Thanks to you guys for joining us, and we hope to see you all again very soon.